Today is the fourth episode of our second season. Our speaker today is Dr. Pavel Utkin. He's currently a senior research scientist at the Institute for Computer-Aided Design of the Russian Academy of Sciences and an associate professor at the Moscow Institute of Physics and Technology. Pavel Utkin studies fundamental and applied problems in the field of shock and detonation wave mechanics, flows of a two-phase granular media using direct numerical simulation, and heterogeneous media mechanics models. He's a lecturer of the courses numerical simulation of reactive flows and the simulations of nonlinear processes. He received his PhD in mathematical modeling and numerical simulation from Moscow Institute of Physics and Technology in 2010. And I would like to ask the audience, please mute yourself during the talk of Professor Utkin, and please leave your comments and questions in chat, or you can directly ask the speaker after his talk. Now I will give the time to Professor Utkin. Please go ahead, Pavel. Yeah.
Okay, thank you very much for the introduction. The topic of my presentation is numerical study of shock-to-detonation transition in the curvilinear channels. So I'd like to tell about the problem of detonation initiation. Actually, it's one of the most important, very important problem in detonation theory. It is known from experiments of Professor Lee with co-authors and from simulations of Professor Levin and Markov that critical energy of detonation initiation is a single sole parameter that controls the initiation process only if the duration of the discharge is lower than some critical value. And otherwise, the longer the duration of the discharge, the greater amount of energy is required for the detonation initiation. And also, the special factor can also be used to optimize the initiation process. For example, these are the pictures from Vasil'ev paper, Professor Vasil'ev from Novosibirsk. He considered the problem experimentally, the problem of detonation wave passage from two narrow channels divided by a baffle into a wide channel. And so it was possible to vary the width of the baffle, and so the results were plotted in terms of critical pressure for the detonation initiation. It was shown that actually the usage of specially distributed and homogeneous sources for detonation initiation could be more is more optimal for detonation initiation that one single whole discharge with energy equal to the sum of energies of distributed sources. This is another example. The detonation was initiated by means of distributed discharges. You can see 6 bright points, and actually the energy of each discharger was lower than critical energy of detonation initiation, and so you do not see the cellular structures here. But at the places when shock waves from different igniters collided, you can see the secondary points that could be considered as secondary dischargers, and so you can see the formation of detonation wave in the whole space here. But at the same time, it's obvious that the parameters of such system of specially distributed igniters parameters should be well adjusted. For example, if the radius of this circle on which the igniters are situated will be too big, you won't get detonation. And this picture, the pictures from paper of Professor Dulescu, and the same idea is illustrated from the comparison of 1D and 2D simulations of direct detonation initiation. It was shown that if you perturb the initial condition in the area of initiation of detonation, it is not more effective in detonation initiation. So the special factor can be a very useful instrument for the optimization of initiation process, but the parameters of such system should be well adjusted. This slide shows another very beautiful, I think, concepts of detonation initiation optimization. The left part of the slide correspond to the shock to detonation transition concepts. This picture from is from the paper of Professor Pavel from Semyonov Institute of Chemical Physics. He considered the process of shock to detonation transition due to the additional discharges that were synchronized with the arrival of the passing shock wave. And actually, the shock wave was amplified by these discharges, and he obtained a detonation wave. Later, he proposed to use a special profile of walls of the channel, and so it was the topic of my PhD study, of my PhD thesis, to carry out such simulation and to investigate the mechanism, the possible mechanism of such process. And we also considered the not planar channel but axisymmetrical tube with contraction and expansion. I'd like to say more about these previous results because I see from current studies of different authors that however history repeats itself, and this topic is of interest now. And here you can see another very beautiful concepts. For example, when detonation can be reinitiated using a small obstacle in the channel, white channel, which helps to reinitiate detonation. And also, it also can be considered as some special factor for detonation initiation. And this experiment of Vasil'ev was actually reproduced in simulations in this paper. So the problem about the shock to detonation transition in the passing shock wave. We consider the channel filled with the stoichiometrical propane A mixture, and the incident shock wave Mach number was 3.0. And the idea was that each parabolic profile produce additional focusing of the flow behind in the region behind the leading shock wave, and successive amplification of the shock wave, and somewhere here initiation of detonation occurred. At the same time, if we use general rectangular obstacles with the same blockage ratio of the channel, we did not get the detonation under the same conditions being equal. And then we proceeded with the geometry with contraction and expansion. Actually, it's important to know that this shock wave, incident shock wave, is not just an abstract shock wave. The idea was that such devices can be used to enhance deflagration to detonation transition process. At the final stages of the process, when we have a shock wave ahead of accelerating flame, we can use such geometries to promote the final stages of the process and initiate detonation. So it was just a shock wave from somewhere. It can be thought as a shock wave ahead of accelerating flame. And so if we connect these 2 points, we will obtain phi value, the angle which characterizes this geometry of the contraction. We analyze the process, double Mach reflection, accumulation of the flow, rotation wave. The cone contraction was expansion was used to support detonation. And so we carried out parametrical study to find the geometry, well, an optimal geometry which can provide detonation for the minimal incident shock wave Mach number. And why I show these previous results? because I see it is still of great interest. For example, this is the video of German scientists. Just a few seconds from this video. It's from ResearchGate. It's their pulse detonation combustion chamber, and it's the experimental setup. How is it operate now? You can see this tube with contraction and expansion. They did not use actually parabolic contraction, it's also linear, but this is illustration of the same concept. You see the accelerating flame, shock wave, reflected waves, formation of detonation, detonation wave in the expanding channel, and so on. So it's actually good that those ideas come into practice now. And also, this is another example. It's the paper of Professor Dolescu with co-author, when again, linear shock wave ahead of accelerating flame interacts with different. Actually, it's one of the examples with different obstacles, corners, and so on to provide detonation initiation. So I moved to our current studies, and as another concept for optimization of detonation initiation due to the special factor, we considered the process of detonation initiation as a result of the reflection of the shock wave from the profiled end wall of the channel. The problem was studied in many papers. The main papers are listed here. The thing is that in all these papers, the reflectors of one particular shape or several particular shapes were considered. For example, semicircular or parabolical or wedge, planar or 3D corresponding geometries. And in the studies for different mixtures, different regimes were obtained and classified: mild ignition, transient ignition, strong ignition. And it was shown that detonation can be formed not inside the cavity of the reflector but in the channel, and so on. But none of these works consider more complex case when we have several reflectors on the reflecting wall. And so these experiments were carried out by Professor Vasil'ev from Novosibirsk. He's my co-author. And he used two-section shock tube with high pressure chamber, low pressure chamber, and optical section. And so-called multifocusing system was mounted in the this optical section. Multifocusing system is this model with 4 sides, and each side corresponds to one system of reflectors. So from experiment to experiment, you can rotate your model to obtain different reflectors. These cavities were obtained by milling with the cutter of different diameter and different milling cutter angle. So the diameters 40 millimeters, 20 millimeters, 10 millimeters, and yes, 10 millimeters were considered, and angles of the cutter 45 degrees, 30 and 15 degrees, and also 90 degrees to get general circular case. And if you cut a cylindrical surface by a plane, you obtain elliptical curve. This slide shows some experimental results that we produced in simulations to analyze the mechanisms of detonation initiation in such systems. Actually, the most interesting cases for us was this case, when two specially distributed reflectors are used, and this case when 5 tangent or adjoint reflectors were used. And again, geometries of these reflectors were different for different angles of milling cutter. We get the following experimental data. The mixture was stoichiometrical hydrogen-oxygen mixture under a very low pressure, 0.04 atmospheres. We had ignition delay times for the case of reflection of a shock wave from a planar wall. It's just ordinary results, also available from many other researchers. And we also consider this case corresponding to one big reflector, this case. And as for the multifocusing systems, we consider two points. This point corresponds to the 5 reflectors, in this case, and this point corresponds to 2 reflectors, this case. So experiments show that geometry with true distributed reflectors is more efficient under conditions in this experiment than the system with 5 reflectors. It provides a lower critical Mach number for the detonation initiation. We want to study what is the reason and how does it work. And also, it needs, I should say that among different possible regimes of detonation initiation, in these experiments, there's a strong mode of detonation initiation was studied. This is the statement of the problem from mathematical point of view, from point of view simulations. The most interesting cases were geometries with 2 reflectors and 5 reflectors. Due to the symmetry of the problem, we considered only 1/2 of the channel in height. This is the initial condition of the problem. And we considered 3 different intensities of the leading shock, 2.4, 2.5, and 2.6. And we obtained different regimes of mechanisms of the process. The width of the domain is 30 millimeters, and the length of the channel actually equals to about diameter of the real channel of the experiment. Resolution, we carried out the resolution study. I will show the results, but actually reasonable results can be obtained with about 4 cells per half fraction length in the ZND solution for the simplified actually kinetic model we used. Here's the mathematical model. We use 2D Euler equations with planar geometry. Planar because you see the cross section of the channel of the shock tube in experiment was rectangular, and so in each plane parallel to the side walls we have the same picture. So actually it's 2D geometry, although of course some 3D effects could be here also. We use simplified model. Parameters of the kinetic scheme were chosen from Schultz and Shepard database. Parameters A, Q, E, and so on are presented in this paper for different pressures. So we get the pressure equal about the pressure behind the reflected shock wave if the initial pressure here is 0.04 atmospheres. And this is the ZND solution for such model of chemical kinetics. The specific feature of the numerical approach is that we used full unstructured computational grids. It provides us to consider geometries, any geometries. Actually, there are not many works in which such approach is used for detonation simulations, but some of them are, actually most of them are listed here. We used some kind of grid function reconstruction, so we used the scheme of the second order in time and in space, and some details could be found here. We considered for the verification purposes the case of inert shockwave focusing in the semicircular reflector, and compared qualitatively other results with experiments of Professor Penyaskov and Fedorov and Skius and Klein. And we also use the terminology from here. We have the original reflected wave, secondary or new reflected wave, Mach stem, shear layers, mushroom-like vortices, and so on. We used the data on ignition delay times for the verification purposes also. Actually, this is a classical, typical XT diagram for the reflection of the shock wave from the planar wall. And this is simulation results in the view of 1D distributions of pressure. The blue dots correspond to the incident shock wave, the green to the reflected shock wave. After some time near the wall, we can see the formation of the internal detonation wave, which overtakes the reflected wave with the formation of the leading detonation wave. And we get the simulated ignition delay time about 30 microseconds, while the experimental value of Vasil'ev was about 50 microseconds. And actually, the same order of magnitude. Of course, this value depends strongly on chemical kinetics model. We also consider the case of one of single large reflector, this one geometry, and also this point corresponding to the planar case I have explained, and this one correspond to the to this case. Again, we have the incident shock wave, the so-called secondary reflected wave I have shown for the inert case. And the specific feature here is that the angle of inclination of the track corresponding to the reflected wave changes due to this Mach stem R2, which moves to the symmetry axis of the channel. So it accumulates, and so we can see the orange dots corresponding to the reflected wave with another inclination. And ignition occurs not near the wall, but at some distance from this point, and then detonation is initiated. So here we can see significantly shorter times for the detonation initiation, but also reasonably corresponding to the experimental values. So this means that actually in this region of parameters, the Schulz-Shepard data corresponds actually to the Vasil'ev experiments. Consider now the most interesting cases of initiation process in the geometry with 2 distributed reflectors and with 5 reflectors. In all pictures here and further, lower part correspond to the distribution of temperature, and upper part correspond to the numerical schlieren, absolute value of gradient of gas of the mixture. Consider the mechanism of initiation for this case. Reflected rays R1 and R2 amplifies parameters inside the cavity, and this is an important role of this flat gap between the reflectors. Ignition occurs actually inside the cavity of the reflector. The combustion propagates between these contact surfaces C1 and C2, occupies this region. You can see the actual pressure waves here, and detonation is initiated somewhere in several points near the symmetry axis of the channel, but actually not far from the reflecting wall. The time from the reflection of this wave incident is about 41 microseconds. For this case, we carried out the resolution study. You can see this part of the channel, and we simulated this problem with resolution 3.5, 6, and 10 points per half reaction length in the Deutsch-von solution. And actually, we get that the mechanism of the process did not change with the good refinement. We see all the same structures, actually the same points of detonation initiation, but the time of initiation was a little bit lower. So this case this is the same picture, 40 microseconds, and we do not see initiation. It will occur at 41 microseconds, and for the more detailed grid, you see initiation. So in this case, we see the effect of very slight effect of promotion of initiation process with great refinement. Actually, in this paper, Rulescu combustion flame about detonation paradox, opposite tendencies were obtained, but he considered the process of cellular detonation wave propagation. It's actually much more complex process than just the initiation of detonation due to reflection of the shock wave. And in case of cellular detonation propagation, the less detailed grid provide faster numerical flames and quite contrary initiation across easier on the less detailed grids. And here's the I said that we considered three Mach numbers: 2.4, 2.5, and 2.6. So I begin with 2.5, and then I will consider 2.4 and 2.6. So for the 2.5, for the second geometry with 5 tangent reflectors, you can see again this reflected wave from this small flat part. So parameters here inside reflectors actually differs from parameters in these reflectors. But here the ignition regions are much more complex. You see the combustion in very thin layers. But however, detonation is initiated at the same moment, 45 microseconds, than for the case of two reflectors. But it occurred somewhere inside the cavity of one of the reflectors. So we can see that for the Mach number 2.5, there is no visible difference between two geometries in our simulations. Maybe if we use if we will use another chemical kinetic schemes more accurate, we will see such small effects as 0.01 in Mach number. For the Mach number 2.4, we did not obtain the strong detonation initiation. Of course, the one-stage chemical model in use sooner or later will provide detonation initiation, but we follow, for example, the criterion from paper of Gelfand. They considered they considered if the initiation occurred when the reflected shock wave moved more than diameter or 2 diameter of the channel, it is a transient mode of detonation initiation. And in Vasil'ev experiment, we know that, and he believed that he analyzed strong detonation initiation. So these pressure waves from this flame will provide detonation, but on the time scales that are not beyond the limits of our actually kinetics model and our consideration. So the case Mach number 2.4 is considered as detonation failure. The very interesting case was obtained for the incident shock wave Mach number 2.6. When this incident shock wave is stronger, when this shock wave is stronger, for this geometry, reflectors do not affect each other. There's no interference between them before the detonation initiation. So detonation was initiated here independently, and in this sense, each of this reflector can be thought as a separate igniter in the specially distributed scheme. If we remind our initial purpose to consider the system from point of view of detonation optimization. And as for the 5 reflectors, again, we see the mutual interference between these reflectors. They affect each other, and again, detonation is situated somewhere near the cavity of one of the reflectors. But in this case, the time from the beginning of the process up to detonation initiation is really longer than in this case. So we can see that if the incident shock wave Mach number is greater than 2.5, 2.6 now, we see that this geometry indeed works better than this geometry. So to conclude my talk in the part of actually all my all my talk, but this conclusion is about part with multifocusing system. So the mechanisms of detonation initiation in the multifocus system of two types, with two semi-elliptical reflectors with a part of flat wall distributed reflectors and 5 adjoining semi-elliptical reflectors are investigated, and the spatial diversity of the reflectors and the presence of a flat wall or part for the geometry of the first type with two reflectors gives different modes of initiation for the larger and smaller Mach numbers of the incident shock wave. And we obtained that for the lowest Mach number 2.4 initiation didn't occur. For 2.5, both multifocus system provides initiation, and for the Mach number 2.6, the geometry with two reflectors works better. And actually, I cannot say that we get just the same as the experiment, but we obtained that the critical, but we obtained that actually the geometry with two reflectors works better if we consider Mach number greater than some critical value. The same we get and we see in experiment. I'd like to say my talk was based on my report at the last IGDRS with some additional features, and the results are published in Shockwave's paper, and you can see and you can find more details about the study here. Actually, that's all. Thank you very much for your attention. I'm ready to answer your question if you have questions.
Yes. Hey, thank you. Thank you for your interesting talk. Yeah, it's very clear. Yeah, I guess my co-host Shem, he just joined because he had to teach a class. So sorry about that. And I guess I will moderate the question session. I will. Let me see. I don't see any question right now written in the chat. Is there any question from the audience? I would like to have you either directly ask Professor Utkin, or you can write your comment or question in chat. Yeah, if there is no question, I have a question or just a clarification. Just this method you used to resolve complex geometry, is it like a cut cell method or?
No, we used geometry. It's a general approach with, but not with curvilinear grids. The grids are unstructured, but they correspond to the curvilinear boundaries of the computational domain. We have the Cartesian grid methods for our simulations. Another topic of interest for me is direct numerical simulation of two-phase flow. So we have such approach, but we did not use it here for such simulation.
Okay, because I'm just interested at the, like when you show this 5 reflectors case, then you have this very sharp tip with 2 curved reflector connected. Like how is it kind of like that to resolve the physics or the wave dynamics around that tip? Is it sensitive to the method you use to implement the complex geometry?
In some simulations we have to lower the approximation order of the scheme in a few number of triangles near such specific features of the geometries. In this, near these corners, you can in about 3 or 5 triangles use just first order scheme to avoid difficulties. It's possible, of course, to get troubles in these points. But nevertheless, the numerical approach is quite robust, and we do not see any problems.
Okay. Okay, I see. Yeah.
Thanks. I have a question. I apologize. I missed most of your talk because I was teaching. But are you considering looking into the detonation initiation or combustion initiation with these these focusing spots?
The goal is to obtain detonation initiation. So initially we obtained ignition in several hotspots, or actually yes, and then it goes to detonation.
And are you able to extract some sort of critical energy or something like that, a minimum shock strength?
Yes, we obtained. We considered 3 Mach numbers, and you see, it's difficult to. It is possible. There are several possible regimes of detonation initiation. You can obtain detonation initiation for different Mach numbers, but in different regimes. You can also obtain detonation initiation in the same system for the lower Mach number, but for longer times, and for completely different regimes. You should take into account viscosity effects, turbulence, and so on. So we concentrated on the strong detonation initiation mode, and so we considered the Mach numbers about 2.5 for the stoichiometrical hydrogen-oxygen mixture. So we do not try to describe all possible regimes in our numerics.
Okay, thank you very much. I think we have a question in the chat. If you want, I'll read it out.
Yes, I can ask it I can also ask it. That's fine. I just had a small question on the CPU time that let's say one simulation took. I might have missed that, and as well as the direction scheme that you used.
The reaction scheme is just one overall simplified model described by this is the one single equation for the reactions. Z is the mass fraction of the reactive component, and that's it. It's a simplified model with parameters from Schultz and Shepard database. And as for CPU time, actually we have the parallel realization of such program, but fortunately the initial pressure of this mixture is very low. So the half reaction length is rather big in comparison, for example, with the same mixture and atmospheric pressure. So the total number of the nodes of the cells was not fantastic. It was about several millions. So it was not very time-consuming simulations, several hours maybe. Due to the relatively small geometry of the problem and to the low pressure, we get the necessary resolution with not very big amount of total number of computational cells.
Okay, and have you looked at all at like more complex reaction schemes, or?
Yes, we also consider more complex schemes. For example, the kinetics of Peterson-Hansen. We carried out the same simulations, and we see that actually the mechanisms are the same. The quantitative difference is about 20% maybe. It's the effect of the real kinetics in comparison with the one stage overall.
Okay, thank you. That was very enlightening.
Hey, Pavel. Hello?
Yes, I hear you.
Okay, great. I was just going to ask a quick question about the curvature at the curvature of the end reflectors. Is there some interesting aspect of modifying the critical curvature at which the reflectors are set at to see its effect on the initiation process? I mean, there has to be some maximum curvature where the effect is probably most prominent. Any thoughts on that?
It's a very interesting question. Thank you. I don't know the answer. We did not study this question. Actually, we follow the experiments in this case, and the experiments were carried out for some particular number of geometries, and I don't think that they were obtained from the consideration of some critical curvature. So I think it can be a question for the further study.
Yes, great. Yeah, it could be an interesting problem in terms of, I mean, obviously, if it's too broadly curved, it won't have too big an effect. But if the curvature is too high, you would expect it to be equally as damping. So, yeah, anyway, great. Thank you.
We try to consider not reflectors like this, but we try to rotate it 90 degrees. And also we obtained very interesting regimes, but we do not have experiments to compare with. And actually, it's possible we have a number of results that are not published. We think about them.
Great. Sounds good. Anyway, good talk. Thank you.
Hi, I have a quick question. Maybe I missed it, but was there a comparison between the experimental results and the computational results? It seemed like there was some experiments going on.
We compared several ignition delay times for verification, and the main comparison was qualitative and quantitative. But in experiment the effect was very small, about several hundreds of the Mach number. In simulations, at least using one-stage kinetics, it's very difficult to differ such small effect. But we considered 2.4, 2.5, and 2.6, and we have shown that at least qualitatively the reason why this geometry can works better than this geometry. In this sense, at least we can compare it with the experiment, and in the range of the Mach number from 2.5, we see that critical Mach number is about from 2.4 and 2.5. But the more detailed comparison, it was not our goal to get the correspondence in this the second digit after the point. We were interested in the mechanisms of the process that could be in experiment.
Got it. Sorry, I missed that before. Thank you.
Pavel, I just have another quick comment. I just probably you guys have already realized that this just with this one-step Arrhenius approximation for chemistry, it might be a bit hard to actually pin down the critical condition, or if you want to further investigate what Dr. Short just suggested for this critical curvature, I believe use this single step Arrhenius might be kind of difficult, because you always have like a non-zero reaction rate at even very low temperature. I believe like rather than like all the way jump to this complex detailed chemistry, maybe a 2-step or 3-step with like a thermally inert or thermally neutral inert induction zone. Maybe that's I don't know, like physically enough for you to better pin down the critical condition, right? Like a 2-step or maybe 3 steps.
The previous report of my PhD student Yaroslava was about analyzing the 2-stage chemical kinetics model, and actually we also the works of Professor Dulescu, in which this model was adjusted to the real mixtures. So the parameters for the real mixtures for the 2-stage model are known. Yes, we also interested and think which model is more suitable for such simulations, not to use the whole mechanism again. Also because we see that the qualitative effect is not so big, so maybe it's not necessary to use the whole model.
Right. Okay. Thank you. Very, very interesting.
I have also one very long question.
Yeah, I think that's from Professor Higgins. Like, I don't know if he wants to ask directly or you want us to read?
Yeah, maybe I could just try to shorten it a little bit. So it's just, I think, very interesting experiment, and it raises the question, what is the optimal spacing and geometry of these artificial hotspots to promote detonation? And at some condition, you would think it would be connected to the detonation cell size. So I think in the experiments you were doing, you were looking at how to promote initiation. So you were using relatively weak shocks, but if very strong shocks were used that were comparable, so the post-shock state was comparable to the post-shock state of a detonation, might hypothesize that the optimal spacing would turn out to be similar to the cell size. In other words, detonation cells are nature's way of promoting detonation, and that if you try to artificially induce detonation with a strong shock, you might find the same spacing. So do you have any speculation as to what you think would happen, or is there a way you could show that the detonation cells are the most optimal way to promote detonation?
Thank you for your comment and question. Actually, we work with Professor Vasil'ev, and he believes that detonation cell size is, well, the most important parameter, and the single actually most important parameter. I explained that the history also of the study, and the relatively weak shock waves are came from another field, and I think maybe if you consider stronger shock waves, it would be very interesting to find the correlation between the spacing and the detonation cell size. I can also I can only thank you for a very good idea. Maybe we will study it.
Thank you. Thank you for the answer.
Is there any other questions or comments from the audience? If not, then I guess, yeah, let's thank our speaker, Professor Pavel Utkin, again for his very interesting talk and for his time preparing this talk. And we were looking forward to his future studies, and also from other people in the group.
I am very surprised, actually, because of such very fruitful discussion.
Yeah,
thank you very much.
Yeah, I hope that
the questions were very, very useful.
Yeah, thank you. Yeah, and also thank for all the our colleagues from the audience for providing these good comments and advices for our speaker. Yeah, hope that's hopefully this will be the point, or the how this young researchers forum works, just to collect everybody's idea, and we can exchange our thought even during this year that we cannot have a chance to meet each other in person. Yeah. Thank you again for your time, and thank everybody for coming today. And in 1 week we have another talk. This time will be from Professor Wenhu Han from Beijing Institute of Technology to talk about ozone sensitization on the DDT problem. Yeah, and hope to see you all next week. And we will distribute the poster, and also we will edit the video of Professor Utkin's talk, and after that we will upload that to YouTube. Thank you all, and have a good day, and have a good night, Pavel. Okay.
Bye.
Thank you very much, Pavel.
Yeah. Bye.
Thank you.
Bye. See you.